Hey everybody, Mr. Tima here, going to talk to you about atomic, nuclear, and particle physics. This is a two-part section. This will be the much shorter spot. The nice part is the next part's a little bit longer, but it's a lot of review. So there you go. Here we go. All right. So basically, you've probably heard of this term, plum pudding model. Okay, you should have learned about that in chemistry, and it all has to do about the center of the atom. Basically, we didn't know at one point what the center of the atom was. We didn't know what was in there, what was going on. We know that there's a nucleus now and that the electrons were at the outside, but there was this guy named J.J. Thomson, and he didn't know that before, or before that, we didn't know that. Okay, now, in American terms, we call it the plum pudding model. Sometimes in IB, they call it the raisin bun model. In America, we don't use raisin buns. I doubt any of you have ever eaten a raisin bun. You've probably had a blueberry muffin, whatever. The idea, though, is if I have my muffin, oh goodness, that is a horribly drawn muffin, but you can go with it. When we split this muffin open and we tear it open, like if we say that now this is like half of that muffin, oh goodness, horrible, right? We don't know where the blueberries that are inside that muffin are, okay? We open it up and there's all these little specks of where the blueberries were. Well, originally we might see one blueberry on the outside here, maybe a little bit, but we didn't know where all the blueberries were. So again, they call that the raisin bun, the plum pudding model, the banana pudding model, the jello with fruit model, whichever way you want to talk about it. All right. So there were Geiger and Marsden. They worked for Rutherford. They showed that atoms are mostly empty space. So a lot of times they're going to ask you a question, or a lot of times people are going to ask you a question two different ways. They're going to say, what do most of the particles do? Well, most of the particles, as we shoot particles through a piece of gold foil, which was called the gold foil experiment, excuse me, I kind of skipped over that. But most of the particles go straight through, or basically kind of go just a little bit away from where they were, but most go straight through. A very small amount will bounce straight back or deflect at a small angle. Okay? This again was called the gold foil experiment. Okay, basically it proved that there was the nucleus of an atom. Okay, so almost 90% of all the particles just went straight through. Some deflected at small angles, but less than 1%, probably even less than 1% of 1%, came back at a very large angle because it hit the nucleus and reflected back. We're going to do a simulation on this. That is part of your work. We'll get to that, though, a little bit later. All right. So nucleus, this whole idea. Well, we also need to talk about the electrons on these shells. So we got to go back to the idea of the Bohr model. And just as a quick refresher, the Bohr model is 2, 8, 8, 8. The idea that we can hold 2 in the first shell, 8 in the second, and 8 in the third. That's why if you look at the first three periods, those are the rows across a periodic table, you'll notice there are 2 in the first row, there are 8 in the second, and 8 in the third. But the whole idea is, when an electron lives on these shells, when it gets really excited, it jumps from one shell to the other. And when that happens, it releases energy. Well, there was this man named Planck, okay, and he developed what's called the Planck's constant. And that is to help determine with a change in energy of an electron. So when this energy jumps from here, let's say it had an energy of 3 and it jumps to an energy of 1, we'd say the difference is 2. Well, if we know the frequency of that light, or if we know Planck's constant, we can then determine the frequency of that light, or what color of light will be emitted. Okay, again, what happens? Why do they jump down? Again, it all goes back to circular motion, centripetal force, the electrical attraction, this whole idea that both attraction, force, everything goes to the center of an object. So the electrons are attracted to the nucleus partially because of circular motion. Okay, this should look very familiar. This is your Roy G. Biv. Here's our red all the way up to the Biv, to the B. That's the color spectrum. Well, the color spectrum of these photons as they're called, are because of these electrons jumping. Well, guess what? The smallest change in energy is right here. Well, the smallest change in energy is red light. And if you actually think back to waves, it has the longest wavelength. Okay, it has the longest wavelength. So since it has the longest wavelength, it has the lowest frequency, it doesn't have as much energy. So that's why the lower is the red. Well, up here, it's the biggest jump. It's the skydiver. It's the high jumper off of the pool. Since it's the highest, it has the most energy change, which again reduces or produces a higher frequency. And since that happens, all right, we get the BIV, the blue, the indigo, and the violet light. Okay? All right. Energy, again, though they produce the difference in light, this jump produces different colors of light. As in wave, energy is related to the electron's amplitude, not its frequency. So just because, even though we talked about how the frequency of a wave changes the actual light spectrum, it actually has to do with the amplitude. And the amplitude is the amount of energy of that jump. Again, if we looked at this block, though, let's just pretend I'm an electron up here for a second on the top block. How many jumps can I make? Well, the answer is it could jump here. That'd be 1. It could jump, it could jump down here. That'd be 2. It could jump down to here, which would be 3. It could jump down here, which is 4. Or it could jump all the way down here, which is 5. That guy could make 5 jumps. The one below it could only make 4 jumps. 1, 2, 3, and 4. Again, here it could only make 2 jumps. 1, 2. They can't jump up. We don't say they jump up. They would gain energy and kind of come up here. But when we say they make those jumps, they can only jump down the ladder. Okay? All right. So when a photon is released, every time an electron drops an energy level. Well, that's where the aurora borealis comes. Basically, the energy from the sun comes and touches the atmosphere of the Earth, and by that happening, it excites the electrons in our atmosphere. With refraction, there's some other things involved there, but it produces a photon or light. Photons are just electrons that are light beams. That's all it is. A photon is a fancy electron that produces light. Okay? And then again, here's our Planck's equation with Planck's constant. So what do we need to be able to do with this? Well, it's really simple. You have to also remember that there was this guy Einstein, right? And he said that E equals mc squared. Okay? And remember that all comes from the speed of light. This is the speed of light. And the speed of light is 3.0 times 10 to the 8th meters per second. Okay, that's a constant. That's the speed of light. Why did I put negative? It's positive. That's a constant, meters per second. And then we have mass, and then we have energy. Well, if you think about it, though, the speed of light is just the speed of whatever we're looking at. And light is a wave. And if we remember, the velocity of a wave is frequency times wavelength. And we learned about that in waves. Well, if our velocity of any visible light is 3 times 10 to the 8th, then basically this equation is just the speed of light equals frequency times wavelength. It's the same thing. It's just the speed of light is the same as velocity of this wave because we're talking about visible light. Okay, first of all, this is 700 N. N means nano, and that's times 10 to the negative 9th. Okay, times 10 to the negative 9th, whatever that number. So this would be 700 times 10 to the negative 9th. All right, so it basically says, hey, what is the amount of energy produced from this red light wave or this light that's at 700 nanometers? Well, if you notice, we need to get the frequency because we have to get to this equation. Okay, we're trying to calculate energy. This H is a constant, okay, and F is frequency. Well, how can we determine frequency? Well, we know the speed of light right here. We know this wavelength. So every time you're given a wavelength, you know the speed of visible light. Bam, we can get the frequency. Okay? And now, once we know the frequency, we can now plug that frequency in with Planck's constant, and we get this joule. Okay? That's how much the joule of one single electron, is Let me erase that real quick. There we go. One single electron is for that amount of red light. So now, goodness gracious, sorry, I'm bouncing around. The energy in that electron is right here. This is 1.7 times that amount of joules. In other words, it's 1.7 electron volts. And where do we get that? We take that number, and we divide it right here, and we rock and roll. Okay? So we'll be ready to go on that as we get to that section. How did I messed up my little pen thing. There we go. All right. So absorption of light, again, this is just a refresher. Again, if you wear red lens glasses, that means that those lenses are absorbing. They are absorbing the red light. Okay, yellow lens glasses absorb the yellow light. So like people that wear yellow glasses tend to be people like on motorcycles or driving cars at night, things like that. Again, it all comes down to E equals mc squared. Eventually, as we move into the next section, we're going to be more worried about this mass component, not just the frequency of light. All right, that's it. We are not going to do the SOCUS problems for this section. We are only going to do these 6 problems right here. Remember, the answer key to that is located online, so make sure you're checking your answers. Until next time, Mr. Tima, out.